Stars are one of the most fascinating objects in the universe. They come in a variety of sizes, colors, and temperatures, and they all have unique characteristics that make them stand out. In this article, we will explore the different types of stars and how they are classified. Stars can be classified based on their size, temperature, and luminosity. The most common classification system is the Morgan-Keenan (MK) system, which was developed in the 1940s. This system categorizes stars into 7 different types, based on their temperature and spectral characteristics. The first type of star is called O-type stars, and they are the hottest and most massive stars in the universe. These stars have surface temperatures of over 30,000 Kelvin and emit large amounts of ultraviolet radiation. O-type stars are also very rare, making up less than 1% of all stars. B-type stars are the next type of star, and they are also very hot, with surface temperatures between 10,000 and 30,000 Kelvin. These stars are very bright and blue, and they emit large amounts of ultraviolet radiation. A-type stars are the third type of star, and they are slightly cooler than B-type stars, with surface temperatures between 7,500 and 10,000 Kelvin. These stars are white or blue-white and emit a lot of visible light. F-type stars are the fourth type of star, and they are slightly cooler than A-type stars, with surface temperatures between 6,000 and 7,500 Kelvin. These stars are yellow-white and emit less ultraviolet radiation than hotter stars. G-type stars are the fifth type of star, and they are the most common type of star in the universe. Our own Sun is a G-type star, with a surface temperature of around 5,500 Kelvin. These stars emit mostly visible light and have a yellow color. K-type stars are the sixth type of star, and they are cooler than G-type stars, with surface temperatures between 3,500 and 5,000 Kelvin. These stars emit less visible light and more infrared radiation. M-type stars are the seventh and last type of star, and they are the coolest and smallest stars in the universe. These stars have surface temperatures below 3,500 Kelvin and emit mostly infrared radiation. In addition to the MK system, there are other classification systems used by astronomers to categorize stars. One such system is the Harvard Spectral Classification System, which categorizes stars based on their spectral characteristics. Apart from the MK and Harvard classification systems, there are also other ways to categorize stars. For example, stars can be classified based on their mass. High-mass stars, which are typically O-type and B-type stars, have masses greater than 8 times that of our Sun. While low-mass stars, which are typically M-type stars, have masses less than 0.5 times that of our Sun. Stars can also be classified based on their evolutionary stage. Young stars are still in the process of forming, while mature stars are in a state of equilibrium. Where the force of gravity pulling the star inward is balanced by the pressure from the star's core pushing outward. As stars age, they evolve and change, eventually becoming red giants or supernovae. The classification of stars is an important tool for astronomers, as it helps them to understand the physical properties of stars and their role in the universe. For example, by studying the properties of different types of stars, astronomers can learn about the conditions that led to the formation of the universe and how stars evolve over time. In addition to studying individual stars, astronomers also study groups of stars, such as star clusters and galaxies. By studying these groups, astronomers can learn about the distribution of stars in the universe and how they interact with each other. Moreover, the study of stars is not only important in astronomy but also in other fields, such as astrophysics, planetary science, and astrobiology. The physical properties of stars, such as their temperature, luminosity, and composition, are crucial for understanding how planets and other celestial bodies form and evolve. For example, the study of exoplanets, or planets outside our solar system, relies heavily on our understanding of stars. As astronomers use the properties of stars to infer the properties of orbiting planets. In addition, the study of stars can also provide insights into the potential for life in the universe. Stars play a critical role in the habitability of planets, as their radiation and energy output can affect the climate and atmospheric composition of nearby planets. By studying the properties of stars, astronomers can identify potentially habitable planets and search for signs of life beyond Earth. In recent years, advances in technology, such as space-based telescopes and high-performance computing, have revolutionized the study of stars. These tools have allowed astronomers to detect and study stars that were previously too faint or distant to observe. In addition, new techniques for analyzing starlight and characterizing exoplanets have led to a wealth of new discoveries and insights into the nature of stars and their planetary systems. One exciting area of research in the study of stars is the search for habitable exoplanets. With the discovery of thousands of exoplanets in recent years, astronomers are now able to search for planets that may be similar to Earth in terms of their size, temperature, and distance from their star. To do this, astronomers study the light from stars, looking for changes in brightness that may indicate the presence of a planet passing in front of the star, known as a transit. By studying these transits and other properties of exoplanets, astronomers can determine whether a planet may be habitable. Another area of research in the study of stars is the study of stellar evolution. As stars age, they evolve and change, eventually running out of fuel and either collapsing to form a black hole or exploding in a supernova. By studying the life cycles of stars, astronomers can learn about the processes that shape the universe and the elements that make up everything around us. The study of stars also has practical applications here on Earth. For example, the light emitted by stars is used in a wide range of technologies, from telecommunications to medical imaging. In addition, stars provide a natural laboratory for studying the behavior of matter and energy under extreme conditions, such as high temperatures and pressures. Another important aspect of the study of stars is their role in the formation and evolution of galaxies. Stars are the building blocks of galaxies, and their formation and evolution are intimately linked to the growth and structure of galaxies. By studying the properties of stars in different regions of galaxies, astronomers can learn about the processes that shape the structure and dynamics of galaxies. In our vast and mysterious universe, there are countless celestial bodies ranging from tiny asteroids to massive stars, and everything in between. One of the most fascinating aspects of these celestial objects is their size and mass. In this article, we will explore the dimensions and weights of planets, stars, and other celestial bodies. Let's start with the smallest members of our solar system, the dwarf planets. There are currently 5 recognized dwarf planets in our solar system: Pluto, Eris, Haumea, Makemake, and Ceres. These small objects range in size from Ceres, which has a diameter of 590 miles, 940 kilometers, to Pluto, which has a diameter of 1,471 miles, 2,370 kilometers. Their masses range from Ceres, which weighs about 0.00016 times the mass of Earth, to Pluto, which is 0.0022 times the mass of Earth. Moving up in size, we come to the planets. There are 8 planets in our solar system, starting with the smallest, Mercury, and ending with the largest, Jupiter. Mercury has a diameter of 3,030 miles, 4,880 kilometers, and a mass of 0.055 times that of Earth. While Jupiter has a diameter of 86,881 miles, 139,822 kilometers, and a mass of 318 times that of Earth. The other planets, in order of increasing size, are Venus, Earth, Mars, Saturn, Uranus, and Neptune. Beyond our own solar system, there are countless other planetary systems with planets of varying sizes and masses. In 2018, astronomers discovered an exoplanet named HD 21749b, which has a diameter about 3 times that of Earth and a mass about 23 times that of Earth. In contrast, the largest known exoplanet is Dennis PJ 082303.1 to 491,201b, with a mass estimated to be 28.5 times that of Jupiter. Moving on to stars, these celestial bodies are much larger and more massive than planets. Our own Sun, a relatively average star, has a diameter of about 864,938 miles, 1,392,000 kilometers, and a mass of about 333,000 times that of Earth. However, there are much larger stars out there. The largest known star, Scuti, has a diameter of about 1,708 times that of our Sun. There are other celestial bodies such as black holes and neutron stars. Black holes are formed when a massive star collapses in on itself, creating a region of space with such strong gravitational forces that nothing, not even light, can escape. The mass of a black hole is measured in terms of its Schwarzschild radius, which is the distance from the center of the black hole at which the escape velocity exceeds the speed of light. For example, a black hole with a mass of 10 times that of our Sun would have a Schwarzschild radius of about 30 kilometers, 18.6 miles. Neutron stars are formed when a massive star collapses and the remaining core becomes so dense that its protons and electrons combine to form neutrons. Neutron stars are incredibly dense, with masses similar to that of our Sun but diameters only about 12 miles, 20 kilometers, across. In addition to planets, stars, black holes, and neutron stars, there are many other types of celestial objects that have unique sizes and masses. One such object is a white dwarf, which is the remnant core of a star that has exhausted its nuclear fuel. These objects are incredibly dense, with a mass similar to that of our Sun but a diameter only about the size of the Earth. Another type of celestial object that has unique size and mass properties is a pulsar. Pulsars are a type of neutron star that emit beams of electromagnetic radiation as they rotate. Due to their small size and high mass, pulsars are incredibly dense and spin incredibly fast. Some pulsars spin hundreds of times per second. We have galaxies, which are enormous collections of stars, planets, and other celestial objects bound together by gravity. The size and mass of galaxies vary widely, with the smallest known galaxies containing just a few hundred stars, while the largest known galaxies contain hundreds of billions of stars. The Milky Way, our own galaxy, has a mass of about 1 trillion times that of our Sun and a diameter of about 100,000 light-years. In addition to the objects already mentioned, there are also phenomena in the universe that do not have a fixed size or mass. One example is a supernova, which is a powerful explosion that occurs when a star reaches the end of its life. The size and mass of the resulting explosion can vary widely depending on the size and type of the original star. Another phenomenon that does not have a fixed size or mass is dark matter. Dark matter is a type of matter that does not interact with light or other forms of electromagnetic radiation, so it cannot be directly observed. However, its gravitational effects on visible matter suggest that it makes up a significant portion of the total matter in the universe. We have cosmic strings, which are hypothetical objects that are thought to have formed during the early universe. Cosmic strings are one-dimensional objects that are incredibly thin but have immense density. The exact size and mass of cosmic strings are unknown, but they are thought to play a role in the formation of large-scale structures in the universe. In addition to the phenomena already mentioned, there are also clusters and superclusters of galaxies, which are among the largest structures in the universe. Galaxy clusters contain hundreds or even thousands of galaxies, as well as dark matter and hot gas, all bound together by gravity. Superclusters are even larger structures, containing multiple clusters of galaxies. The size and mass of clusters and superclusters vary widely, with some superclusters containing thousands of galaxies and having a mass of trillions of times that of the Sun. These structures provide important clues about the formation and evolution of the universe, and studying them can help astronomers better understand the processes that have shaped the cosmos over billions of years. Another fascinating object in the universe is a quasar, which is an extremely luminous object powered by a supermassive black hole at the center of a galaxy. Quasars are among the brightest objects in the universe, emitting huge amounts of energy across the entire electromagnetic spectrum. The size and mass of quasars vary, but they are typically located in distant galaxies and can be billions of times more massive than the Sun. Studying quasars is important for understanding the evolution of galaxies and the role of black holes in shaping the universe. There are cosmic rays, which are high-energy particles that travel through space at nearly the speed of light. The exact sources of cosmic rays are not fully understood, but they are thought to come from supernovae, quasars, and other high-energy events in the universe. The size and mass of cosmic rays are negligible, but their high energy makes them important objects to study. Understanding cosmic rays is important for understanding the fundamental nature of matter and energy, as well as the physical processes that occur in the universe. In addition to the objects and phenomena mentioned, there are also cosmic neutrinos, which are subatomic particles that can travel through the universe almost completely unimpeded. They are created by high-energy events such as supernovae, and they can provide insights into the properties of such events. The size and mass of cosmic neutrinos are very small, but their importance lies in their ability to carry information across the universe. The formation and distribution of nebulae throughout the universe have been the subject of scientific inquiry for many years. Nebulae, which are clouds of gas and dust in space, have played a vital role in the formation of stars and planetary systems. In this article, we will explore the origins and distribution of these fascinating structures. The formation of nebulae. Nebulae are formed from the remnants of old stars that have exploded, releasing gases and dust into space. These clouds of debris can then become condensed and form new stars, planets, and other celestial bodies. The process of star formation is complex and can take millions of years. It typically begins with the gravitational collapse of a dense cloud of gas and dust, which can be triggered by a nearby supernova or other external forces. As the cloud collapses, it becomes hotter and denser, eventually reaching a point where nuclear fusion can occur. This fusion creates the intense heat and pressure necessary for a new star to form. The leftover gas and dust form a protoplanetary disk around the new star, which can eventually form into planets, asteroids, and other objects. Types of nebulae. There are several different types of nebulae in the universe, each with their unique characteristics and properties. The most common types are reflection nebulae. These nebulae are illuminated by nearby stars, which reflect light off their surfaces. They are often blue in color and are commonly found near star-forming regions. Emission nebulae. These nebulae emit light themselves and are often brightly colored. They are typically found around hot, young stars and can be seen as pink, red, or orange. Planetary nebulae. These nebulae are the remnants of old, dying stars. They are named for their round, planet-like appearance and are often brightly colored. Distribution of nebulae. Nebulae are found throughout the universe, but their distribution is not uniform. They are typically found in regions where stars are forming or have recently formed. This includes spiral arms of galaxies, where there is a high concentration of gas and dust. Nebulae can also be found in the outer regions of galaxies, where there is less competition for resources. The study of nebulae is an important area of research for astronomers and astrophysicists. By observing the light emitted by different types of nebulae, researchers can gain insight into the physical processes occurring within them. This information can help us to better understand the formation and evolution of stars, planets, and galaxies. One notable example of the importance of studying nebulae is the discovery of planetary systems beyond our own. In the past few decades, astronomers have been able to detect planets orbiting stars outside of our solar system, known as exoplanets. By studying the properties of the parent stars and the light reflected by their surrounding nebulae, researchers can learn more about the conditions necessary for the formation and evolution of planetary systems. Another area of research related to nebulae is the study of interstellar medium, ISM, which is the matter and radiation that exists in the space between stars. The ISM is composed of various forms of gas and dust, including the remnants of old stars and nebulae. By studying the properties of the ISM, researchers can gain insight into the chemical and physical processes that occur within it, such as the formation of molecules and the energy transfer between particles. In recent years, advances in observational technology, such as space telescopes and high-resolution imaging techniques, have allowed us to study nebulae and other celestial objects in greater detail than ever before. With these tools, researchers can observe the processes occurring within nebulae in real time, providing valuable data for theoretical models and simulations. Moreover, the study of nebulae has also led to discoveries of new phenomena and objects in the universe. For example, the Crab Nebula is a well-known nebula that was formed by a supernova explosion that was observed by astronomers in 1054. The Crab Nebula has been extensively studied by astronomers, and observations have revealed a pulsar at its center, which is a rapidly spinning neutron star that emits regular pulses of electromagnetic radiation. The study of pulsars has provided valuable insights into the properties of matter under extreme conditions, and has even helped to confirm some of the predictions of Einstein's theory of general relativity. Nebulae also have practical applications in modern astronomy. For example, the use of nebulae as standard candles has allowed astronomers to estimate the distance to objects in the universe. Standard candles are objects whose intrinsic brightness is known, allowing astronomers to calculate their distance from Earth based on their observed brightness. Certain types of nebulae, such as type Ia supernovae, are used as standard candles because they have a known brightness and are visible from large distances. In addition to their scientific importance, nebulae have also captured the imagination of people around the world. Nebulae are often the subject of stunning astronomical photographs and artwork, and have inspired countless works of science fiction and fantasy. One notable example is the famous Orion Nebula, which is visible to the naked eye as a faint patch of light in the constellation Orion. The Orion Nebula is one of the most photographed objects in the night sky, and its striking colors and intricate patterns have made it a favorite among amateur astronomers and stargazers. One promising area of future research in the study of nebulae is the search for habitable planets. As we learn more about the conditions necessary for the formation and evolution of planetary systems, we can begin to identify potentially habitable worlds orbiting stars surrounded by nebulae. By studying the properties of the nebulae and their impact on planetary formation and evolution, researchers can gain insight into the likelihood of finding habitable planets in our galaxy and beyond. Another area of research is the study of the interaction between nebulae and their environment. Nebulae can influence the surrounding interstellar medium, and can be affected by other celestial bodies such as black holes and galaxies. By studying these interactions, researchers can gain a better understanding of the complex physical processes occurring within nebulae and their impact on the evolution of the universe. Furthermore, The study of nebulae can also shed light on the origins of life in the universe. The interaction between the universe and energy sources is a fascinating topic that has captured the imagination of scientists and the public alike. The universe is a vast and complex system that is composed of various elements and energy forms. These energy sources are integral to the functioning of the universe and have a significant impact on our lives. One of the most important sources of energy in the universe is the Sun. The Sun is a massive ball of gas that generates energy through the process of nuclear fusion. This process releases a tremendous amount of energy, which is then radiated into space in the form of light and heat. The Sun's energy is essential for life on Earth as it provides the energy required for photosynthesis, which is the process by which plants convert sunlight into food. Another source of energy in the universe is gravity. Gravity is a fundamental force that governs the motion of all objects in the universe. It is the force that keeps the planets in orbit around the Sun and the stars in orbit around the center of their galaxies. Gravity is also responsible for the formation of stars and planets, as it causes gas and dust to collapse in on themselves, creating new celestial bodies. Dark matter and dark energy are two other sources of energy that are essential to the functioning of the universe. Dark matter is an invisible form of matter that does not emit or absorb light, but its presence is inferred from its gravitational effects on visible matter. Dark energy is a mysterious force that is causing the expansion of the universe to accelerate. While the exact nature of dark matter and dark energy is not yet fully understood, they are believed to make up a significant portion of the universe's total energy. The interaction between these energy sources and the universe is complex and fascinating. The energy released by the Sun powers the motion of the planets and provides the energy needed for life on Earth. Gravity shapes the universe and governs the motion of all celestial bodies. Dark matter and dark energy play a significant role in the evolution and expansion of the universe, although their exact nature remains a mystery. Understanding the interaction between the universe and energy sources is essential. For scientists to gain a better understanding of the universe's evolution and to develop new technologies that harness these energy sources. From solar panels to gravitational wave detectors, our understanding of the universe and its energy sources is critical to our technological and scientific progress. Moreover, the study of the interaction between the universe and energy sources has significant implications for our understanding of the origin of the universe itself. The Big Bang Theory, the prevailing scientific theory on the origin of the universe, postulates that the universe was created in a massive explosion that released a tremendous amount of energy. This explosion is believed to have created all the matter in the universe, including the stars and galaxies that we observe today. The study of the cosmic microwave background radiation, a remnant of the Big Bang, has provided scientists with valuable insights into the early universe's conditions. The energy released during the Big Bang is also believed to have created the fundamental forces of nature, including gravity, electromagnetism, and the strong and weak nuclear forces. The understanding of these forces is crucial for scientists to develop a unified theory of the universe that can explain all the fundamental interactions. Furthermore, the interaction between the universe and energy sources has significant implications for the search for extraterrestrial life. One of the essential conditions for life as we know it is the availability of energy. Scientists are searching for habitable planets that have the right conditions to support life. These planets must be at the right distance from their star to receive the right amount of energy to support life. The search for extraterrestrial life is not limited to planets in our own solar system but extends to other stars and galaxies. The development of new telescopes and technologies has allowed scientists to study the universe's energy sources in more detail and to search for signs of life beyond our own planet. Moreover, the interaction between the universe and energy sources has also led to the development of new energy technologies on Earth. Solar panels, which convert the sun's energy into electricity, are one of the most widely used renewable energy sources. The harnessing of wind energy, which is caused by the sun's uneven heating of the Earth's surface, is another renewable energy technology that has become increasingly popular. The study of the universe's energy sources has also led to advancements in space exploration. The development of ion thrusters, a type of propulsion system that uses electric fields to accelerate charged particles and create thrust, has made it possible to explore deep space with greater efficiency and precision. These propulsion systems are powered by solar panels and are significantly more efficient than traditional chemical rockets. The interaction between the universe and energy sources has also led to new developments in the field of astrophysics. The detection of gravitational waves, ripples in the fabric of spacetime caused by the acceleration of massive objects, has allowed scientists to study the universe in a new way. These waves are generated by the most energetic events in the universe, such as the collision of black holes and the explosion of supernovae. The interaction between the universe and energy sources has also led to advancements in the field of particle physics. The study of subatomic particles and their interactions has allowed scientists to gain a deeper understanding of the fundamental forces of nature, including gravity and electromagnetism. The use of particle accelerators, such as the Large Hadron Collider, has allowed scientists to simulate the conditions that existed in the universe just after the Big Bang and to study the behavior of particles under extreme conditions. Additionally, the interaction between the universe and energy sources has led to new developments in the field of materials science. The study of materials that can convert energy from one form to another has led to the development of new energy storage technologies. For example, the development of lithium-ion batteries, which can store energy from solar panels and wind turbines, has made renewable energy sources more practical and efficient. The interaction between the universe and energy sources has implications for the long-term future of humanity. As we continue to use the Earth's resources to power our civilization, we must consider the impact of our energy use on the environment and on future generations. The development of sustainable and renewable energy sources is crucial to ensuring the long-term survival of our species and the health of our planet. Moreover, the interaction between the universe and energy sources has also led to the development of new strategies for mitigating the effects of climate change. The excessive burning of fossil fuels has led to a significant increase in greenhouse gases in the atmosphere, which has resulted in global warming and climate change. To mitigate the effects of climate change, there is a need to transition from fossil fuels to renewable energy sources. This transition is necessary to reduce greenhouse gas emissions and to ensure a sustainable future for the planet. The transition to renewable energy sources has many benefits beyond reducing greenhouse gas emissions. It can also provide economic benefits by creating jobs and stimulating economic growth. Stars are one of the most fascinating objects in the universe, and their life cycles are equally intriguing. Different types of stars have different life cycles, but all of them start with the same process: the gravitational collapse of a cloud of gas and dust. Let's explore the different stages in the life cycle of various types of stars. Protostars. A protostar is a dense, hot core at the center of a cloud of gas and dust. It is formed when the gravitational collapse of the cloud reaches a critical point. At this stage, the protostar is not yet hot enough to sustain nuclear fusion, which is the process that powers a star. Main sequence stars. Once a protostar reaches a temperature of about 10 million degrees Celsius, nuclear fusion begins in its core, and it becomes a main sequence star. The energy produced by fusion balances the inward pull of gravity, and the star enters a stable phase that can last for billions of years. Red giant. When a main sequence star exhausts the hydrogen in its core, it begins to fuse helium into carbon and oxygen. The fusion reaction produces more heat, causing the outer layers of the star to expand and cool, making the star appear red. The star has now become a red giant. Planetary nebula. As a red giant continues to fuse helium into heavier elements, it expels its outer layers into space, forming a cloud of gas and dust called a planetary nebula. The remaining core of the star is now a hot, dense object known as a white dwarf. Supernova. When a massive star exhausts its fuel, its core collapses under its own weight, creating an explosion known as a supernova. The explosion releases an enormous amount of energy, and the star may briefly outshine an entire galaxy. Neutron star or black hole. After a supernova explosion, the core of the star may either become a neutron star or a black hole. A neutron star is an incredibly dense object that is about the size of a city, while a black hole is an object with such intense gravity that nothing, not even light, can escape from it. Moreover, the life cycle of a star also plays a critical role in shaping the universe around it. For example, the planetary nebulae that form after a red giant star sheds its outer layers contain heavy elements that were created through fusion reactions in the star's core. These heavy elements then become part of the interstellar medium, the gas and dust that fills the space between stars, and can later become the building blocks of new stars and planets. Another interesting aspect of star life cycles is how they impact the search for extraterrestrial life. Main sequence stars like our Sun are considered to be the most likely candidates for hosting habitable planets, as they are stable and long-lived. However, the formation of red giants and supernovae can have a significant impact on the habitability of planets orbiting them. The gravitational pull of a red giant can destabilize the orbits of planets, while a supernova can release harmful radiation that would make life on any nearby planets impossible. Furthermore, studying the life cycles of stars is crucial for understanding the origin and evolution of the elements that make up the universe. Nuclear fusion in the cores of stars is responsible for creating heavier elements such as carbon, oxygen, and iron, which are essential building blocks for planets, moons, and even life itself. These elements are also the basis for many of the chemical processes that occur in our bodies and on Earth. Moreover, the study of the life cycles of stars also helps us to understand the history of the universe. The first generation of stars, for example, were composed almost entirely of hydrogen and helium, with trace amounts of other elements. These early stars lived fast and died young, exploding as supernovae and releasing heavy elements into the interstellar medium. Subsequent generations of stars, including our Sun, were formed from this enriched material, which allowed for the formation of more complex elements and the eventual emergence of life. In addition, the study of the life cycles of stars has practical applications for astrophysics and space exploration. For example, understanding the evolution of stars helps astronomers to develop models for the formation and evolution of galaxies, which in turn can aid in the search for habitable planets and the study of dark matter and dark energy. The study of supernovae, meanwhile, can help researchers to refine their understanding of the origin of cosmic rays and the properties of interstellar gas. Another aspect of the life cycles of stars that is of great interest to scientists is the possibility of observing them in real time. Since stars live for billions of years, studying their entire life cycles is not possible within the lifespan of a human observer. However, there are rare cases where a star can undergo a rapid evolution that can be observed within a human lifetime. One such example is a luminous blue variable, LBV, a rare type of star that can undergo extreme variability in its brightness and temperature. LBVs are thought to be in a transitional phase between a stable main sequence star and a red supergiant, and their extreme variability is thought to be caused by episodes of mass loss. Studying the behavior of LBVs can provide important insights into the mechanisms that drive the evolution of stars, as well as the processes that lead to supernova explosions. In addition to observing individual stars, astronomers can also use the properties of stars to study the properties of galaxies as a whole. By observing the distribution of stars at different stages in their life cycles, astronomers can determine the age and metallicity of a galaxy, as well as its history of star formation. This information can then be used to test theories about the formation and evolution of galaxies, and to refine our understanding of the structure of the universe. The study of star life cycles also has important practical applications for society, particularly in the fields of energy and climate change. Nuclear fusion, the process that powers stars, is a potential source of clean, renewable energy that could help to reduce our reliance on fossil fuels. While scientists have made significant progress in developing nuclear fusion as a viable energy source, there are still many challenges to overcome before it can be implemented on a large scale. The study of stars can also provide insights into the potential habitability of other planets in our galaxy. By studying the properties of stars and their planetary systems, astronomers can determine the conditions necessary for a planet to support life as we know it. This information can then be used to guide future efforts to search for habitable planets and extraterrestrial life. Finally, the study of star life cycles has important implications for the future of humanity. As our own star, the Sun, approaches the end of its life cycle and evolves into a red giant, it will likely engulf the inner planets, including Earth. While this event is still billions of years away, studying the life cycles of stars can help us to prepare for the long-term future of our planet and our species. Moreover, the study of star life cycles can also help us to better understand the origins of life on Earth. The heavy elements created in the cores of stars are thought to have played a crucial role in the formation of the first organic molecules and the emergence of life. By studying the evolution of stars and the distribution of heavy elements in the universe, we can gain insights into the conditions that led to the emergence of life on our planet. In conclusion, the study of star life cycles is a multifaceted area of research that has implications for. In conclusion, the study of star life cycles is a multifaceted area of research that has implications for our understanding of the universe, the history of the cosmos, the practical challenges facing society, and the long-term future of humanity. From the search for clean, renewable energy sources to the search for extraterrestrial life, the study of stars offers a wealth of opportunities for scientific discovery and innovation.
The universe is a vast and mysterious place, filled with countless celestial bodies that have been colliding with each other for billions of years. These collisions have played a vital role in shaping the universe as we know it today. In this article, we will explore some of the most significant collisions that have occurred in the universe. One of the most notable collisions in the universe is the collision between galaxies. Galaxies are massive collections of stars, gas, and dust held together by their own gravity. When galaxies collide, their mutual gravitational forces cause them to merge into a single, larger galaxy. These collisions can take billions of years to complete, and the resulting galaxy can have a dramatically different appearance than its predecessor. Another significant collision in the universe is the collision between stars. While stars are much smaller than galaxies, they still pack a significant punch when they collide. When two stars collide, they can release enormous amounts of energy, including X-rays and gamma rays. These collisions can also produce new elements that were not present in either star before the collision. Planets and moons can also collide with each other in the universe. These collisions can create craters and impact basins, as well as change the orbits of the objects involved in the collision. The most famous example of a planetary collision is the one that formed the Moon. Scientists believe that a Mars-sized object collided with the Earth about 4.5 billion years ago, and the resulting debris formed the Moon. Asteroids and comets are also common objects that collide with other celestial bodies in the universe. These collisions can have devastating effects, as demonstrated by the asteroid impact that wiped out the dinosaurs about 66 million years ago. Comets are also known to collide with planets and moons, leaving behind large impact craters and sometimes even causing mass extinctions. Additionally, collisions in the universe are not just limited to physical objects. They can also occur between particles, such as protons and electrons, during events like solar flares and coronal mass ejections. These collisions can result in the release of high-energy particles and radiation, which can have significant effects on Earth's atmosphere and the technologies that rely on it. Another interesting type of collision in the universe is the collision between black holes. Black holes are some of the most massive objects in the universe, with gravitational forces so strong that not even light can escape their pull. When two black holes collide, they can create gravitational waves, ripples in the fabric of spacetime that travel outward through the universe. The first detection of gravitational waves was made by the Laser Interferometer Gravitational Wave Observatory, LIGO, in 2015, and since then, many more detections have been made. These detections have allowed scientists to study black holes and their collisions in unprecedented detail, providing new insights into the physics of the universe. Despite the destructive power of collisions in the universe, they also play a crucial role in the formation and evolution of celestial bodies. Through collisions, new stars and planets are born, and old ones are destroyed, paving the way for the next generation of celestial bodies. The study of collisions in the universe is, therefore, an essential part of understanding the history and future of the cosmos. One of the fascinating aspects of collisions in the universe is that they can also create conditions for the formation of life. The collision of comets and asteroids with planets can bring water and organic molecules, the building blocks of life, to previously sterile environments. It is believed that such collisions may have contributed to the emergence of life on Earth and other planets. Moreover, collisions between galaxies can also trigger the formation of new stars, providing the conditions necessary for the emergence of life. These collisions can create dense regions of gas and dust, which can collapse under their own gravity, forming new stars and planetary systems. These new systems can harbor planets that may have the right conditions to support life. The study of collisions in the universe is not just about understanding the past and present of the cosmos. It is also critical for predicting and mitigating potential collisions with Earth. Scientists are constantly monitoring asteroids and comets that may pose a threat to Earth, and studying their properties can help us develop strategies to prevent catastrophic collisions. In addition to their impact on the formation of life, collisions in the universe also provide important insights into the fundamental laws of physics. When two celestial bodies collide, they release a tremendous amount of energy, which can be observed in the form of electromagnetic radiation and gravitational waves. Studying these emissions can help us understand the nature of matter, energy, and the fundamental forces that govern the universe. Collisions involving black holes, for example, can provide a unique opportunity to study the properties of spacetime and gravity. When two black holes collide, they create a distortion in spacetime that can be observed as gravitational waves. Studying these waves can provide insights into the properties of black holes, such as their mass and spin, and can help us test the predictions of Einstein's theory of general relativity. Furthermore, studying collisions in the universe can also provide valuable information about the origins of the universe itself. The study of the cosmic microwave background radiation, the leftover radiation from the Big Bang, has revealed that the universe underwent a period of rapid expansion known as inflation. Collisions between cosmic particles during this period are believed to have played a critical role in shaping the early universe and its evolution over time. Moreover, collisions in the universe are not just limited to physical interactions between celestial bodies, but they can also involve complex interactions between different forms of matter and energy. For instance, collisions between high-energy particles in the universe can lead to the production of new particles, including exotic particles such as dark matter and supersymmetric particles. Studying these particles and their properties can help us unravel the mysteries of the universe, including the nature of dark matter, which is believed to make up a significant portion of the universe's mass. Additionally, these collisions can also provide important insights into the early universe and the conditions that existed shortly after the Big Bang. Furthermore, collisions in the universe can also have significant implications for our future as a species. While the likelihood of a catastrophic collision with Earth is relatively low, the consequences of such an event would be devastating. Therefore, developing strategies to mitigate the impact of such collisions is crucial for our long-term survival. One approach being pursued by scientists is to develop technologies to deflect asteroids and comets away from Earth's path. This involves using spacecraft to nudge the celestial body onto a new trajectory that avoids a collision with Earth. Additionally, scientists are also exploring the use of explosives to break up asteroids and comets, reducing the risk of a catastrophic impact. Finally, collisions in the universe also have an impact on the evolution of galaxies and the distribution of matter in the cosmos.
The atmosphere is a critical component of any planet. It helps regulate temperature, protect against harmful radiation, and provide gases necessary for life. In the solar system, each planet has a unique atmosphere with varying layers of gases. Starting from the innermost planet, Mercury, its atmosphere is virtually non-existent. It is so thin that it is often considered a vacuum. Because of its proximity to the Sun, Mercury is exposed to intense solar winds and radiation that strip away any gases that may have existed. The next planet, Venus, has a thick and toxic atmosphere. Its atmosphere is primarily composed of carbon dioxide, with clouds of sulfuric acid that create a greenhouse effect. The atmospheric pressure on the surface of Venus is so high that it is similar to being almost a kilometer underwater. The upper atmosphere of Venus has several layers of clouds that create a dynamic weather system, including lightning and hurricane-force winds. Earth, our home planet, has a unique atmosphere that is crucial to supporting life. Its atmosphere is divided into 5 layers: the troposphere, stratosphere, mesosphere, thermosphere, and exosphere. The troposphere is the layer closest to the surface and is where all of Earth's weather occurs. The stratosphere contains the ozone layer, which protects life on Earth from harmful UV radiation. The mesosphere is the coldest layer of the atmosphere, and the thermosphere is where the auroras occur. The exosphere is the outermost layer of the atmosphere and gradually transitions into space. Mars, the next planet, has a thin atmosphere that is primarily composed of carbon dioxide, with traces of nitrogen and argon. It also has clouds of water, ice, and dust. Mars' atmosphere is not thick enough to support liquid water on its surface, but evidence suggests that liquid water may exist beneath its surface. The outer planets, Jupiter, Saturn, Uranus, and Neptune, are known as gas giants because they are primarily composed of gas, primarily hydrogen and helium. Jupiter has the largest atmosphere in the solar system, extending over 5,000 kilometers from the surface. Its atmosphere is known for its iconic Great Red Spot, a massive storm that has been raging for hundreds of years. Saturn's atmosphere is similar to Jupiter's, but it has a more complex cloud system and a hexagonal-shaped polar vortex. Uranus and Neptune both have a relatively thin atmosphere compared to the gas giants, but they are known for their blue color due to the presence of methane gas. Moreover, the study of the atmospheres of other planets can also help us learn about the history and evolution of the solar system. For example, the thin atmosphere of Mars suggests that it may have once had a thicker atmosphere and potentially even liquid water on its surface, making it a possible candidate for supporting life in the past. The study of exoplanets, or planets outside of our solar system, is also an important area of research. By analyzing the atmospheres of exoplanets, we can determine their composition and potentially identify signs of life. For example, the presence of oxygen in the atmosphere of an exoplanet could indicate the existence of photosynthetic life. In addition to their scientific significance, the atmospheres of planets are also important for space exploration. Understanding the atmospheric conditions of other planets can help us design spacecraft that can survive and operate in these environments. For example, the thick atmosphere of Venus and the intense radiation of Jupiter present significant challenges for spacecraft missions. The study of planetary atmospheres is also crucial in understanding the effects of climate change. Earth's atmosphere, for instance, has been significantly impacted by human activities such as burning fossil fuels and deforestation, leading to an increase in greenhouse gases and global warming. By studying the behavior of other planetary atmospheres, we can better understand how our actions are affecting the environment and what we can do to mitigate the effects of climate change. Furthermore, the study of planetary atmospheres has implications for the search for extraterrestrial life. Understanding the atmospheric conditions necessary for life to thrive on Earth can help us identify potential habitable worlds in other star systems. For instance, we know that liquid water is a crucial component for life as we know it. And studying the atmospheric conditions of planets can help us determine whether they have the necessary conditions to support liquid water. In recent years, significant advancements in technology have allowed us to study planetary atmospheres in greater detail than ever before. Spacecraft such as the Mars Atmosphere and Volatile Evolution, MAVEN mission and the Cassini-Huygens mission to Saturn have provided valuable insights into the atmospheric conditions of these planets. Ground-based observatories, such as the Atacama Large Millimeter/Submillimeter Array, ALMA, in Chile, have also contributed to our understanding of planetary atmospheres through observations of the radio emissions they produce. Another important aspect of studying planetary atmospheres is the potential for developing new technologies and materials. For example, the extreme conditions of Venus' atmosphere, with high temperatures and pressure, have led scientists to develop materials and technologies that can withstand these conditions. These advances can have applications in fields such as aerospace engineering and materials science. Furthermore, understanding the dynamics and behavior of planetary atmospheres can also have practical applications in weather forecasting and climate modeling. By analyzing the complex interactions between different layers of the atmosphere and how they affect weather patterns, we can improve our ability to predict and prepare for extreme weather events. The study of planetary atmospheres is an exciting area of research that continues to yield new discoveries and insights into the universe around us. With the ongoing exploration of our solar system and the development of new technologies, we can expect to uncover even more fascinating details about the atmospheres of other planets and what they can teach us about our own planet and the universe at large. Another important aspect of studying planetary atmospheres is the potential impact on space exploration and colonization. Understanding the atmospheric conditions of planets can help us determine their habitability and identify potential resources that can be used for future missions or even colonization. For example, the discovery of water ice on Mars suggests the possibility of extracting water for use by future explorers and colonists. Moreover, the study of planetary atmospheres can also aid in the search for new propulsion technologies that can enable faster and more efficient space travel. Scientists are currently exploring the use of electric propulsion systems that can ionize gases in the atmosphere of a planet to provide thrust. This technology could potentially be used to facilitate travel and exploration of other planets in our solar system and beyond. The study of planetary atmospheres is essential in expanding our knowledge of the universe and our place in it.